Welcome to the 39th session in the first module of the course Signals and Systems. We had embarked upon a discussion of commutativity and associativity in the previous session, and in this session we intend to complete our discussion on what was left, namely associativity. Now, we had brought the proof that convolution was associative up to the following point. Let me enunciate what we got on both sides, the left hand side and the right hand side. Let me put it down. So, we continue the proof of associativity of convolution, and essentially what associativity says is x1 convolved with x2 and then convolved with x is the same as x1 convolved with the result of convolution of x2 and x. We will call this the left hand side and we will call this the right hand side, abbreviated by LHS and RHS. Now, the left side evaluated at the point n is essentially summation k and summation L, and the right hand side again evaluated at the same point is summation k1 and summation L1. Now, we need to make a correspondence here, and that is what we are going to do. So, this is the correspondence between k and L1 is clear. And we also need to make a correspondence between L minus k and k1. So, let us do that. L1 corresponding to k and k1 corresponding to L minus k. So, of course, n minus L1 minus k1 would correspond then to n minus k minus L minus k, which is n minus L, and this agrees with the left hand side expression. Moreover, when k and L in fact both independently go from minus to plus infinity, as you can see here, take k first. So, you have k going from minus to plus infinity. If k goes from minus to plus infinity, then of course L1 goes from minus to plus infinity. And now fix k. With a fixed k, when for every k, for every fixed k, when L goes from minus to plus infinity, then so does k1. k1 also goes from minus to plus infinity. So, therefore, kl independently going from minus to plus infinity implies and is implied by k1 L1 going from minus to plus infinity, and in fact they are equivalent. So, therefore, when we make this correspondence, we notice that we have exactly the same expression. So, we have nothing left to do in the proof. We have the same range of summation, we have the same expression, and therefore, the left hand side is equal to the right hand side. So, let us write it here. With this correspondence, the left hand side is equal to the right hand side, and hence we have proved what we wanted to prove. Now, we need to look at the continuous case. That requires a little more explanation. The idea is the same, but it requires a little bit of explanation. In fact, it requires bringing in what is called a transformation of element of integration, and here we are talking about a two-dimensional integration. So, we have to be a little careful. Let us do that now. It is not very difficult, but we need to complete it, and there we go. So, for the continuous case, let us write down the left hand side and the right hand side again. Left hand side, x1 convolved with x2 and then convolved with x3, and right hand side, x1 convolved with the result of convolution of x2 and x3. And let us evaluate the left hand side at a particular continuous value t. And to do that, we will first begin by evaluating x1 convolved with x2 at the point t. Very simply, it is x1 lambda multiplied by x2 t minus lambda d lambda going from minus to plus infinity. And then we have x1 convolved with x2 and then convolved with x3 evaluated at t being x1 convolved with x2 evaluated at alpha multiplied by x3 at t minus alpha integrated with respect to alpha from minus to plus infinity. And now we need to substitute for this from the previous expression, x1 convolved with x2 at t. Let us do that. So, that is essentially, so now we have a double integral, x1 lambda multiplied by x2 alpha minus lambda multiplied by x3 t minus alpha integrated with respect to alpha and lambda. It is a double integral. Each of alpha and lambda independently go from minus to plus infinity. And let us similarly write down the right hand side. The right hand side requires first an evaluation of x2 convolved with x3 at the point t, which is very easy. Let us make it lambda 1 here, just to distinguish between the previous lambda in the left hand side, then x1 convolved with x2 convolved with x3 first, evaluate at t is x1 alpha 1, x2 convolved with x3, evaluate at t minus alpha 1, integrated with respect to alpha 1 from minus to plus infinity. And that can be rewritten as a double integral again. So, there we go. We have a double integral again, and we need to make a correspondence again between the integrals. Let us identify the correspondence. We have them all on the same page. We can identify the correspondence. So, it is very clear that lambda needs to correspond with alpha 1. I will show them in different colors. So, I have alpha minus lambda corresponding to lambda 1. So, let me write that down, lambda 1 and alpha minus lambda, and lambda and alpha 1. So, let us put this down in a matrix form, the transformation that we require. We have alpha 1 is equal to lambda, lambda 1 is equal to alpha minus lambda. Let us write that down in the form of a matrix. Now, when we want to transform the element of integration d alpha 1 d lambda 1 and express it in terms of d lambda d alpha, what we need to do is to consider the determinant of this matrix. We need to consider the determinant of this. Now, that determinant is very easy. That determinant is in fact equal to 1 in magnitude. That is what we are interested in. We are really interested in the magnitude of the determinant, and therefore, what we have is that d alpha 1 d lambda 1 by what is called the Jacobian property. We involve the Jacobian, which is the absolute value of this determinant. So, by the Jacobian principle, d alpha 1 d lambda 1 is equal to 1 times d lambda d alpha. And of course, when alpha 1 and lambda 1 independently go from minus to plus infinity, that also corresponds to alpha and lambda independently going from minus to plus infinity. And now, if we go back to the previous two expressions that we had, let us see them. Once we make these correspondences, the red correspondence and the green correspondence, what happens to this? What happens to the argument of x3? Let us put that down in blue. So, when we make this transformation, if alpha 1 is to be replaced by lambda and lambda 1 by alpha minus lambda, then t minus alpha 1 minus lambda 1 would become t minus lambda minus alpha minus lambda, which is essentially t minus alpha, and that agrees with this, and therefore, the two integrands correspond exactly, and we have just seen that because of the Jacobian principle, the elements of integration correspond exactly, the limits of integration correspond exactly, and therefore, the left hand side is equal to the right hand side, and we have proved the associativity of convolution. Now, what does this mean? Convolution is commutative, convolution is associative, both for the discrete and the continuous case. It is a very powerful idea. In fact, we have used it before. This is not the first time we are hearing this, but I wanted to go through a formal proof to round things off, And now what we will do is to say a little more about the typical kind of systems and certain consequences of commutativity and associativity in the next session. So, let us meet again in the next session, where we shall say a few more things about linear shift invariant systems in general, both in discrete and in continuous time. Thank you.